Dear participants, on behalf of Physics Department, it is my pleasure to welcome you to a fourth international seminar entitled Pedestrian Journey from Classical to Quantum Concepts. This seminar will be conducted by Professor Gupta sir, who is expert in theoretical nuclear structure physics and high energy physics. He pursued his PhD at Delhi University under the mentorship of Professor A.N. Mitra sir. And his quest for knowledge then led him to Harvard University, and he worked as a postdoctoral associate with Nobel laureate Professor S.L. Glashow. Today, he serves as an emeritus professor in the Department of Physics, Punjab University, Chandigarh. Throughout his illustrious career, which began in 1980 at Punjab University, Professor Gupta has made significant contribution to hardonic physics and flavor physics. Among his many achievements, he was one of the first to discover the mixed nucleon wave function, a crucial development in explaining neutron charge structures. He also co-developed the chiral constituent quark model with configuration mixing, which has provided key insight into the proton spin crisis. His work in the flavor physics, particular in the area of quark and lepton mass matrices, CP violations, neutrino oscillations, which are internationally recognized. Professor Gupta ongoing continue to push the boundary of our understanding with over 150 publication in top-tier journals and gathering more than several thousand citations. Beyond his research, Professor Gupta has played pivotal roles in academic community, including serving as chairman of Department of Physics at Punjab University, UGC coordinator for Center of Advanced Study in Physics. He has also been a member of prestigious committees such as Physical Research Committees of CSIR and many more. Before I hand over to our esteemed speaker, I would like to mention that this seminar has received an overwhelming response with more than 280 registration from over 50 reputed institutes in India and 5 different countries. We are confident that Professor Gupta's insight will provide invaluable learning and inspiration for all participants. Thank you for joining us. And now over to Professor Gupta, sir.
Good morning, everyone. My dear students, well, I am here to receive a lot of questions from you. Because see, giving lecture is very easy, but asking question is little more difficult. But answering question is still more difficult. But I would be very, very happy if you ask any or every question, wise or unwise. But as a student, you have a privilege to ask questions. And let me tell you, the doubts can be cleared only when you ask questions. If you don't ask questions, you will hear the seminar or lecture and forget after some time. This is not true. This is true about me also. True about everyone. Anyway, no, let me first start with the topic. The topic of the day is pedestrian journey from classical to quantum concepts. Pedestrian means पैदल चलने वाला. पैदल चलने वाला मतलब आराम से चलता हो. मतलब आराम से आप क्वेश्चन पूछिए, आंसर मिलेंगे उनके. That's how you will understand. And let me tell you, quantum mechanics is very, very simple if you follow this path. If you don't follow this path, you read as many books as you like. I have attended hundreds of seminars. It only adds to confusion. Very rarely you see you get a kind of clarity which you want. So anyway, with this brief comment, I will start, and I will start from the very basic. If you have any question about that basic also, you can still ask me, and you can interrupt me as many number of times as is possible. Don't worry, I have enough time. I have come here to clear the doubts. कोई time की restriction नहीं है, ठीक है? Okay, so let us start with my next slide is what is physics? Okay, let me start with what is physics, because half of the doubts come from the fact that people don't know what is physics. And if you understand physics, then the doubts will start clearing up. So what is physics? The name originated from the Greek word physicos, natural, and physis, nature. So considered as synonymous of natural philosophy until the late 19th century. In fact, physics was considered natural philosophy because that is how it developed, just a nomenclature. But anyway, more importantly than that, it is certainly the oldest and the most pure sciences, because the observation of the things around and understanding what we are made up of, this is how the physics started. And that is obviously the most basic. So it is considered with mathematics, physics, and chemistry, and of course some other sciences we consider physical sciences. But physics was because physics provided basis to the chemistry also. So chemistry can be understood only if you understand physics. That is how the electron behaves in the atomic and molecular system. That's how the chemistry is understood. Okay, so traditional definition, study of matter, energy, and relation between them. So this is how we teach you physics. Here physics means this is the relation, but it goes beyond that. Okay, no, see, once we try understand physics, then obviously we will have to have the scientific method, and that is where it is different from other observations. There's a scientific observation which we have to keep it in mind, and that is what I will elaborate, and that is what will remove the confusion about the quantum mechanics also. Okay, so what is the scientific method? Information data gathered by careful observations. Careful observation means there is a method through which you observe, and that method is specified. So you collect the data. Now, this is true for any physics. This is at the very fundamental, you can say, level of physics. So you collect data, and then what happens? A preliminary generalization hypothesis formed. Somebody forms a, you can say, some empirical relation, or maybe some formula, or maybe some hypothesis. Well, all these things we do in research also. But it is true at any level. Even in your laboratory also, you do the same thing. That is what we teach. Of course, we don't emphasize that. So once you have taken the data, a preliminary hypothesis formed, hypothesis tested by further observation experiments. See, one of the key things in physics is once a hypothesis is formed or made, then it has to be cross-checked by future observations. If your hypothesis bear the brunt of the future observations, then you have discovered a new formula, or you have discovered a new theory also, if it is a very wide range of data. Okay, so then conclusions are drawn. So once you have find that the hypothesis satisfies the, you can say, future data or future observations, then we say we can draw the conclusions. The conclusions are agreement, hypothesis accepted as a scientific theory. The scientific theory or hypothesis is one and the same thing. In physics, in research, we sometimes call phenomenology also. That phenomenologically, it is accepted model. And if it is disagreement, modified, discarded, or thrown out. You understand? No, let me summarize. No, if you understand this, you have understood everything in physics, particularly quantum mechanics. I will come back to it towards the end of the lecture to emphasize that all understanding of quantum mechanics or any other theory basis hinges on this thing or based on this thing. So observation is the key thing, as you notice in science. Okay, so let us try to go further. What we proclaim about an object depends upon our tool of observation. How do we observe? So next question is, how do we observe? Think over it. Most of the time, we observe through light, scattering of light. That is how historically we had done it. Now, of course, the observation domain also keeps expanding. I'll delve on this thing as we proceed further. You understand? See, earlier, in the earlier 20th century, the only tool of observation was light. We used light to observe. And of course, I am observing you through light. You are observing me through scattering of light or reflection of light, whatever you want to call it, you can call it. We shine light on an object. A part of it is reflected back, which corresponds to the color of the object seen by us. This is very simple, right? All of us would agree. And there is no difficulty in this and understanding this. A body which absorbs whole of light falling on appears black. So light which is absorbed completely, see, black body is not that it has black color. It is because the light is absorbed by it. So that's how we infer that it's a black. There's no black color as it is. The colors are, of course, because we know that the light gets, if we have an orange color, then the orange light gets reflected. And the red color, red light gets reflected. So that's how it is. That's how we observe it. No, we know, even classically, it was known the electromagnetic spectrum. And you already know about it in detail. What is the electromagnetic spectrum? If you see that visible light is only a small part. So this is the, you can say 700 nanometers to 400 nanometer is the visible spectrum. I don't have to explain it. For 400, I remember that in the angstroms also, 400 angstroms to 700 angstrom would be, we do teach it in the BSc level, in fact, experiments also. This is the, in fact, Newton rings, for example, and others, BSc level experiments, it is known that the visible part of the spectrum. But the entire electromagnetic spectrum is very wide, is very small part. You can see that I have shown the visible part is only this thing, but it starts from frequency. If you measure in terms of frequency, it starts with 10 to the power 4, the smallest frequency, and goes up to 10 to the power 20. So 16 orders of magnitude. Similarly here, wavelength nanometers, 10 to the power 15, very long, and this is the shortest. In fact, gamma rays correspond to that. And similarly, X-rays, ultraviolet, infrared, microwave, FM radio, TV, and AM radio. So these are the long wavelengths, and this is a visible part of the spectrum. So visible part of the spectrum is very small. And when we develop our understanding, we keep the visible part of the spectrum in mind. Keep this question in mind. Is it right? If whatever we observe through visible part of the spectrum, it gets embedded in our mind. And we think that the entire universe should be revolving around that. I don't think that that is right, because that is our limitation. Ultimately, we have to consider the observation can be from we have to consider the entire spectrum if we believe in scientific observation. It so happens that human body or we as humans, we have limitation to observe the spectrum, only that part of the spectrum which our retina is sensitive. But it doesn't mean that the other part of the spectrum doesn't constitute the observation process. Now, the point is, once the observation process expands, then we start observing newer and newer phenomena. So let us proceed further. Okay, so let us see when we proceed further. If I want to observe, if I want to utilize the entire spectrum of observation, that is from gamma rays to radio waves, then we may observe a lot of new different things which are not visible to us. So what we do when we expand this, I will give you a very simple example which students can understand. Suppose I ask you how the hills look when we observe it through our visible light. We find that it is like this, and mostly it is green, right? But if you observe it through telescope or binocular, the view changes completely. Similarly, if I ask you to how the sun looks to be a bright disk type of object. If we see it through our naked eye, although I recommend that one should never see it, maybe in the morning and in the evening. In the morning, it looks red, and in the evening, also, it looks red. In between, it is very bright. But then, if you observe it through other means, it becomes more complicated. If you go near it, it becomes still more complicated. If you try to probe the interior of the sun, we don't know much except through indirect experiments, through gamma rays and neutrinos coming out of that. So the point is, as the tools of observations expand, we tend to observe newer and newer phenomena. And there is no need that when a particular hypothesis, which is made for a particular part of the observation tools, should be the same elsewhere also. Okay, let us try to use the example of the light itself again. Now, suppose I shine light. Say, shine a light of wavelength, say 500 angstroms on a pellet. Pellet means some piece of 1 gram pellet of and an electron, and compare it with an electron. The electron is a very small object, and you know the atom is made up of electron and nucleus and so on and so forth. Proton, neutrons in the nucleus, and electrons are around that, right? Okay, so what would be the difference? So when I observe, okay, so I think there is some problem with the marker. Okay, so when I observe a pellet, its energy is 10 to the power 13.3 electron volt. I measure in terms of the electron volt, it is 1 gram is equal to so much, right? And when the light falls on it, it is not at all disturbed, right? You will agree with me because the energy corresponding to this is very small. I think there is some. The energy corresponding to this is less than electron volt. So less than electron volt energy interacting with 10 to the power 33 electron volt, you will find that it doesn't make a much difference to that. But let us see the electron. The electron energy is so much, and when this light falls on it, if I have to see, first I can't observe this electron through this kind of wavelength. I have to use a light of larger frequency or larger energy, right? Photons of larger energy. I will explain that in the next slide. Okay, so now thus reflection of visible light is suitable tool for observing our daily life, macroscopic objects. But as we have seen, microscopic objects are greatly disturbed by the process of shining light on them. Reflection light cannot be used for observing them. Because you know that objects which are larger, light can be reflected from those. If the objects are smaller, then the light may not be reflected from them. The light may scatter from them, right? Okay, I'll explain it further. Tool is to study the diffraction pattern. So how do we understand objects which are very small by the scattering of light? And you know that there's a diffraction or interference phenomena. When the objects interfere lights, then the diffraction takes place. And the diffraction, condition for diffraction is wavelength should be of the order of the dimensions of the object. No, size of the atoms is order of 10 to minus 10 meters. And to observe diffraction pattern, wavelength should be of the order of 10. In fact, smaller than that. Electron has to be smaller than the atom. And it has to be 10 to minus 12 or minus 14 meters, right? For observing electron. You are understanding this point? This is very crucial point. So what I am saying is, for observing daily life objects, 1 gram pellet, we need visible light, we can see it, observe it. But if I have to observe atom can be observed by scattering of light because it's very, very small compared with the wavelength. Then the wavelength has to be comparable to that. This is all classical physics, right? This is, I think, should not be difficult for any student to understand. Diffraction takes place only when the wavelength is equal to the size of the object. So for that matter, so this corresponds to X-rays or in fact gamma rays in the electromagnetic spectrum. That is why X-ray diffraction patterns are important tool in structure elucidate atom. To observe atoms, X-rays are needed, but to observe structure of atom, we need gamma rays or wavelengths which are shorter than the X-rays. Or in other words, if you have to observe an electron with a gamma ray, and gamma ray, have energy of few MeV. So you are hitting an object or trying to diffract an object of few electron volt or maybe 0.5 MeV with some maybe 10 or 15 MeV. And that means that object would be violently disturbed. So this is the crucial point, that when we try to observe microscopic objects, any means or any method of observation would violently disturb that. This is physical reality. We have to live with this. Our visible light is not a suitable tool to observe atomic structures or microscopic structures. So is that point clear to all the students? That with visible light, we have limited ways of observations. But if we increase the observability to increase the domain of knowledge, then we have to go to the other part of the spectrum. And if we use the other part of the spectrum, then at the microscopic level, a lot of disturbance can take place compared with the macroscopic objects. Now, this is what you have to keep it in mind. So to observe smaller and smaller objects, we need light of smaller and smaller wavelength. Using the formula E is equal to hc by lambda, smaller wavelength calls for higher energies. Explain the fact that it was difficult to probe smaller objects in ancient times. The earlier times, that's why it took time to discover the microscopic object, to discover atoms and molecules, apart from the formulas from chemistry and all that. But physical observation of atoms and molecules could be observed only in the early 20th century through X-rays and gamma rays. Now, this is, if we let us try to understand what is classical physics. Classical physics, all kinds of branches, mechanics, sound, light, heat, etc. So, in fact, mechanics and electricity includes these things also, because electricity, mechanics, light is ultimately electromagnetic waves. Therefore, it is mechanics and electricity which governs most of the classical physics. Now, before proceeding further, let us try to understand what is classical mechanics or classical physics. Let's not limit ourselves to mechanics. What is the key, you can say, inputs which we don't discuss in the classroom? What are the key assumptions of classical physics? And the key assumptions of classical physics are: each object is infinitely divisible. That is, there is no fundamental constituents of matter. This is a fundamental assumption. In fact, when we teach, you consider that infinitesimally divisible, small part of the matter. If we have to apply forces, we say consider a small part which is infinitesimally small. Now, this is an assumption which goes in all classical mechanics works or classical mechanics fields. well-defined trajectories. So because of the fact that when we were dealing with macroscopic objects, we could photograph the trajectories. What is the meaning of trajectory? It means you can specify the position and the momentum of the particle at any time. And it is infinitesimally small particle. This is the assumption which goes again in all part of the classical mechanics, whether you are doing statistical mechanics. This is a fundamental assumption, which again we don't emphasize. Causality, cause always precedes effect. This is also understandable. There has to be cause for observe something else to be observed. I can't go into it because it will take a lot of time, but I understand that most of you will understand. The cause always precedes effect. Determinism. There is no bar on the accuracy of observation. It means when classical physics developed, matter is infinitesimally divisible. Well-defined trajectory means determinism. That you assume that as the tools of observation become more and more refined, you can reach at more and more accurate results. However, all these assumptions were only at the macroscopic world level. Nobody has checked these assumptions at the microscopic level. This is the big catch. No infinitesimal divisibility. Nobody had observed atoms, but we know that once you have atoms, they are made up of nuclei and electrons. And again, those electrons and nuclei are somewhat divisible, but electron we know even at the present level of our understanding, it's a fundamental object. It is not divisible further. Proton neutrons are made up of quarks, etc. But classical physics never assumed that there are fundamental constituents of matter. So this is a sort of, you can say, false assumption at the microscopic level. At macroscopic level, it works. Similarly, if we go down, determinism. No, I have just shown that if you have to observe atomic level phenomena, then there is an inherent disturbance. And that inherent disturbance cannot be overcome by any means or method. You will say, okay, let me observe through neutrinos. Then you say, oh, I can prove that even with neutrinos, the basic disturbance would be there. You observe through any other particle. There is no way. You cannot go out of this thing because it's very fundamental. The whatever is the energy of the object to be measured, the corresponding wavelength or frequency has to be there for the observation. Now, if you understand it, that means these assumptions of classical physics were okay. Number one, each object is infinite. So this is not, may not be true at the microscopic level. Similarly, well-defined trajectories, again, this may not be true at the microscopic level. And see, third, of course, fourth also, there is no bar on the accuracy observation. There could be limitation when we go to the microscopic world. So I don't find anything surprising about it. This is a limitation which is there, which is there. The limitation is because the way nature is there. So there is nothing. इसमें क्या अचंभे की बात क्या है? कुछ नहीं है. आप if you look at the hills and you go near the hills look different. There is nothing wrong with that. Nothing surprising about it. Similarly about the sun also. Similarly about black hole. If I ask you the question, what is inside the black hole? There is no way you can observe it. So it's all a hypothesis. Because if you throw light, the light is absorbed. It is never scattered from black hole. You throw particles, they are also absorbed. So you will always have indirect inferences. Similarly, there are other situations which we just have to hypothesize. We cannot really observe even with our enlarged observation space, unlike the visible part of the spectrum to which human beings are limited to. So if you let me summarize, mostly concerned with matter and energy on the normal scale of observation, objects being observed is never disturbed by the process of observation. So this is the crux of the classical physics. So based on this thing, our all imagination, our mental process are geared onto this kind of hypothesis. Because we are also classical objects. So obviously, if I were quantum object, by now I would be roaming all through the room. I would be jumping here and there. So that is not happening. So I am a classical object because light is not able to disturb me. So that is the crucial part of it. And then we go to the. So this is the crucial part. So as we start concerning about the behavior of matter and energy under extreme condition, that is on very large or very small scale, we start observing new phenomena described in modern physics, or you can say quantum physics, or so on and so forth. So there is nothing unusual about it because the domain of observations have increased. So you start observing new phenomena. And if you observe new phenomena, as per my earlier slide, you have to make a new hypothesis. So what is the big deal about it? No deal at all. Okay, so then there are experimental, because physics is experimental science, and new experiments, when are devised, that lead to new physics. And one of the crucial observation was observation of black body radiation. Black body, you see, let me tell you, in principle, we don't get black body. It's very difficult to make a black body. But any body which is emitting radiation, you can apply this hypothesis. So this was, maybe I should not devote much time on it because most of you have learned it in the normal books. And that is what I would be stating. So I would not be spending too much time on it, so keeping my time for questions and other observations, right? Am I right? Most of you observed that black body radiation cannot be, see, the classical thermal physics could not explain these curves. These curves. If you take a black body and you observe the intensity of light or heat emitted depending on the wavelength. So this curve could not be explained. You had a formula which explained this part and this part, not the entire part. So this was the problem with the black body radiation. This is, of course, Rayleigh-Jean's law and Wien's law. So classical theory failed to precisely agree with the experimental results. So the hypothesis of classical physics could not explain the experimental observation. So we have to go beyond the classical physics. There's nothing we can do about it. Experiments of Rutherford established that an atom consists of heavy positively charged nucleus and negatively charged electrons. If classical picture is adopted, according to Earnshaw, the system will be stable only if electrons are kept revolving the nucleus, similar to planets revolving the sun. So this is some kind of stability you can ensure. But the electromagnetic, you can say, laws tell us that if a particle is accelerated, then it emits radiation. A particle which is moving, you know that any particle is moving in a circle, it is always under acceleration, right? This is clear. That means if you make a model of an atom where a central heavy positively charged part around which the electrons are revolving, then they will have to emit radiation as per the classical laws. So once it emits radiation, that means its path would become shorter, its radius will become shorter and shorter. Ultimately, it will merge with the center. Or in other words, the stability and the structure of the matter could not be explained through the classical physics. And let me tell you, this is nothing unusual about it. The classical mechanics was never designed for microscopic particles. So why should we be surprised about it? There is no surprise about it. As far as I am concerned, it is some new phenomena you have to discover. So the classical physics failed to explain the stability of atom. Photoelectric effect, again taught at the BSc level, and it's very crucial experiment. Einstein got Nobel Prize for this. And this, in fact, proved something very interesting. And what was that interesting? What is the phenomena? See, whenever you want to understand anything in physics, First, you should see what is the phenomena. What is the experiment about? There is always a phenomena associated with an effect, photoelectric effect. So that effect is characterized by phenomenon of ejection of electrons from a metal plate when light of suitable wavelength of light falls on it. These are, and what are the experimental facts? And then you have to, this is the phenomena, and what are the observations? That is what you have to keep it in mind. The observations are no photo emission if frequency of radiation is below a particular value called threshold frequency. Again, we take it, so most of students know it. Below it, this is experimental fact. Don't correlate. Don't go to the conclusion. ये एक एक्सपेरिमेंटल फैक्ट था कि आप डिफरेंट वेवलेंथ की लाइट जो उस पर फॉल करते हो एक फ्रीक्वेंसी के बिलो वो इलेक्ट्रॉन इजेक्ट नहीं हो रहे. दिस इज एक्सपेरिमेंटल फैक्ट. Stopping potential emitted electron depends on frequency and not intensity. Kinetic energy and stopping potential and emitted electron depend on frequency and not intensity. This is another important. And third is, of course, the instantaneous emission. Then what is the meaning of instantaneous? It means there is no time lag. Once light shines on the metallic surface, and it immediately the electrons are ejected. These are all observations. No, question is, again, this is a microscopic phenomena because electrons, etc., were not part of classical physics. No, once you have this kind of thing, then how do you explain it? And interestingly, in classical physics, we could not explain it. Maybe I should mention it. In classical physics, you know that the energy depends on the amplitude and it doesn't have frequency dependence. So electrons are ejected depending upon the frequency, right? So obviously sufficient energy is not transmitted to the electrons below a particular frequency. But classical physics says that it doesn't matter frequency, the energy transfer process is frequency independent. So that is where is the importance of the, you can say, this threshold frequency comes. According to classical theory, light has a wave character having its energy proportional to square of amplitude, that is intensity and not frequency. Thus, classical theory cannot explain the experimental facts about photoelectric effect because instantaneous emission also. Classical theory would say that the energy transmitted slowly. Once the electrons acquire energy which is sufficiently greater than its binding energy, it will get ejected, right? So therefore, classical physics could not explain the photoelectric effect, particularly the threshold frequency and instantaneous emission of the electrons. There is another lot of spectroscopic data. See, when light is emitted, so you can say that the in terms of classical physics, electromagnetic theory, the radiation is always emitted in a continuous manner. There is no discontinuity in according to classical physics. But when the radiation was emitted by atomics, we found spectra, atomic spectra. That means they are discrete lines. So the discrete lines could not be explained by the classical physics. And these are some well-known Lyman, Balmer, Paschen, Brackett, and Fund series. The original spectrum could not be explained by classical physics because there in classical physics there is no provision of these things. Dual nature of radiation. The photoelectric effect could be explained. Einstein explained that if light is made up of photons or it has particle-like characteristics, that's why it is called dual nature. Phenomena like interference, diffraction, polarization can be explained on the basis of wave nature electromagnetic radiation. Phenomena like photoelectric effect, Compton effect, black body radiation cannot be explained on the basis of particle nature, can be electromagnetic radiation. Conclusion, electromagnetic radiation has, no, this is, see, photoelectric effect, you studied that, you assume that the light is made up of photons, then you can explain the photoelectric effect. Compton effect also same way, black body radiation, Planck hypothesis, that light is made up of photons, right? And that's how you could explain the, you can say through classic radiation using that photons. Or in other words, we have the light at that time it was assumed. No, let me make a word of caution. That is where the confusion starts arising. No, instead of talking about it, that the behavior of light, That depends on at what scale you are observing. We started making, you can say the nomenclature was based on the classical physics. Because in classical physics, we kept this wave nature and particle nature as distinct. And that is what creates a lot of havoc in the minds of the students or minds of the experts even, that it's the dual nature. Because the moment somebody says dual nature, you start imagining classical particles. A classical particle है तो वो wave कैसे बन गया वो? And then people make weird models. I remember my teacher telling me something very strange, which was very confusing. So, but actually keep it in mind that light is the same thing. The only thing is we are observing phenomenon at a different scale. And one can expect different behavior, different outcome, and different kind of, you can say, theory also emerging out of that. So keep that point in mind before proceeding further. Dual nature of radiation, whole energy of universe in the form of electromagnetic radiation and matter. Electromagnetic radiation has got a dual character. Nature loves symmetry, so material particles should also have dual character. No, see, basically जब एक बार इस चीज को emphasize कर दिया कि electromagnetic radiation has dual character, then people started talking about कि यार photon light का dual character हो सकता है, तो other particles का भी हो सकता है. So then of course Louis de Broglie put forward a bold hypothesis that every particle has a wave characteristic with it. No, see, this is something, this hypothesis fitted into the broader frame. But then what I see when I will talk about quantum mechanics, one would need not call it say dual nature or something of that sort. We will get rid of all this duality problem, and it can be very easily got rid of it. Actually, आप सोचो कि जो इलेक्ट्रॉन का वेव फंक्शन की या वेव एसोसिएटेड विद इलेक्ट्रॉन was discussed, that was through scattering experiments. And scattering experiments we teach at MSc level. We assume that the electron has a particular wave function. We don't have to say it's a wave. We can say its characteristics are described by some kind of wave function, which looks similar to wave theory. But that is not equivalent to saying that electron is the wave. And that is what creates confusion. Okay, let me proceed further. So what is the wave particle duality? See, I'm covering all the issues which are discussed in the books. The wave particle duality states corresponding to every particle, there is a wave associated with it and vice versa. Or particles have wave nature and waves have particle nature. This is also, and this is even now people talk about it, even in the case of quantum field theory or anything which you discuss, people always talk of this thing, that the corresponding particle and so on. So the language is very confusing and at times it creates problems. Okay, so as I mentioned that if we want to observe microscopic world, then what you find, there's an inherent limitation in the observation. And that inherent limitation is coming from the fact that the tools through which we observe microscopic world are as large or as small as the object to be measured. It's like this, that if you try to observe someone with a big ball, or say heavy ball, then the person will be disturbed quite a bit. So that means you cannot predict its, you can say, position correctly or momentum if it is moving. Let me tell you, if you use the analogy of the electron, observing it through gamma rays, then if you want to say there is a cyclist and that has to be, say, observed with the impact of some bigger moving vehicle like a truck or a car, you can know what is going to happen. The cyclist would fly out. So you would not be able to do that. The question is that as we go down, as we try to observe microscopic things in the world, microscopic world, we find that the disturbance by the observation process is significant. It cannot be ignored. And the limitation of that was expressed by the Heisenberg uncertainty principle. In fact, it stated that delta E delta T has to be half h cross or h by 4 pi. delta px, delta x, canonically conjugate variables. In fact, we can have a delta j and delta theta. In fact, any canonically conjugate variable, those who study classical mechanics, delta p, delta q has to be greater than half h cross. This is the inherent limitation of the observation process in the microscopic world. अब इसमें क्या मेरे को तो समझ नहीं आता इसमें क्या प्रॉब्लम है. One can understand very easily there has to be inherent some kind of limitation because the observing process is like that. So this is something very important, and then we have to go. No, when we have to next step, which is most crucial. No, one thing is that you don't do anything. Forget that. Okay, I am happy with classical mechanics. I don't have to talk about quantum mechanics. I don't have to develop quantum mechanics. Well, that is not the approach of the scientist. That can be approach of other people, but scientists always want to go beyond what is known and how the unknown part has to be understood in terms of new phenomena, new processes, and so on and so forth. So the scientists thought that we have to go beyond classical physics. अब आप ये बताइए, आपने क्लासिकल फिजिक्स को डिस्कार्ड कर देना है क्योंकि कोई भी फैक्ट उसका क्लियर नहीं है, कोई भी उसकी अजम्पशन ठीक नहीं है माइक्रोस्कोपिक वर्ल्ड में. लेट मी क्वेश्चन यू, इन द माइक्रोस्कोपिक वर्ल्ड, इन द मैक्रोस्कोपिक वर्ल्ड, क्लासिकल फिजिक्स स्टिल वर्क्स because it was designed for that. It is only in the microscopic world that the problem arose. By the way, what is the time? Track of the time. So still there is a sufficient time, right? Okay, so what I have to do? I have to incorporate in the new hypothesis. अब मेरे फर्स्ट सेकंड स्लाइड पे जाइए कि कुछ ऑब्जर्वेशन की हमने. अब उन ऑब्जर्वेशन को हमने इंक्लूड करना है एक हाइपोथेसिस में. उसमें क्रूशियल पार्ट क्या है, क्योंकि सारी ऑब्जर्वेशन को भी आपको रिड्यूस करना पड़ेगा. तो क्रूशियल पार्ट क्या है उसमें कि वेव पार्टिकल, सो कॉल्ड, आई शुड पुट इट इन कोट्स, वेव पार्टिकल ड्युअलिटी, अनसर्टेनिटी प्रिंसिपल, डिस्कार्डिंग द नोशन ऑफ वेल डिफाइंड ट्रैजेक्टरीज. These notions have to be discarded because they are not experimentally verifiable. Uncertainty principle, wave particle duality, these are observations, so you have to incorporate that. अब इनको incorporate करना तो आपको नई theory बनानी पड़ेगी. Do you agree with me? No, what is that new theory? Definition. So before we go to the new theory, we have to define. In physics, we always start with definition. And let me tell you, definition is the most important thing. It is a definition which keeps refining and refining as we go down, as we go to better and better theories, right? So how do we proceed? Now, once this, we have to start. See, physics always starts from some initial inputs. So you have to start with something initial. And that input is that, now we say state of a system. We define a system that any particle, any collection of particle, we say call it a system, right? And then we have to specify it by what we call as the state of the system. And that state cannot be like the classical physics state where trajectories are well defined. This state is different. It is a new beginning, new starting point. So condition is data theoretical, undisturbed motion that is resisted by as many conditional or data as theoretically possible without contradiction. This is just a, you can say, a definition which is without contradiction, but it doesn't reveal you anything, doesn't tell you what state is. That you have to specify or learn through example, like state of hydrogen atom is represented by this. This is how we represent psi h, ls, angular momentum and spin, right? Spin of the electron, right? State of free electron is represented by psi e p s z, not by px, the spin projection and the momentum of the electron. So out of position or momentum, we can choose either of the variables. Generally, we choose momentum because that is observable. It is very difficult to observe the position. So therefore, we observe position. So this is how we represent the state. A state A given state can be thought of as superposition of two or more states, indeed an infinite number of ways. Conversely, no, I think I have to go back. Yes, superposition principle. No, this is the heart of the quantum mechanics. If you understand superposition principle, then you understand almost everything in quantum mechanics. And what is that? The state of the system and the superposition principle. इसके बाद आपको कुछ नहीं डिस्कस करने की जरूरत, wave particle duality, uncertainty, everything is built into it. The quantum mechanics is built into these two facts and the operators. Apart from that, you don't have to bother about anything else. Now, how do we define superposition? By the way, we have superposition in classical physics also. And in classical physics, it is discussed at many places, like superposition of forces, parallelogram law of forces, right? In fact, superposition is there everywhere, even in the Newton law also. That if F is equal to ma, it implies that all the, you can say, particles constituting m, right, object, the forces corresponding that is superimposed upon each other. But that classical superposition is very different. Like parallelogram law of forces, you have two vectors, the result is in between the two. If you have vector like this and this, the result is in between like this. You studied all of that. But in quantum superposition is very different. What is quantum superposition? If A and B are two possible states of system, then a possible state of system is defined like you take even hydrogen atom. If the hydrogen atom can be in two states, A and B, then we can constitute another state of the hydrogen atom or any microscopic system by superposing like that. That there is a state C C equal to A, B, alpha A, beta B, alpha and beta complex numbers. If a measurement is made on the state C of the system, then A times A mod square times we get state of A, and B mod square times we get state B. That means if we make a measurement on the state C, then what would be the result? The result would be alpha mod square times we will get state A, and beta mod square we will get state B. This is very different from the parallelogram law of forces. So this is the crucial difference, and everything is built into this thing. Your wave particle duality, uncertainty, everything is built into this thing. So let us try to a given state can be thought of as superposition of two or more states, a system indeed an infinite number of ways. So alpha and beta can take any values. So therefore, it can be infinite number of ways you can constitute another state of the system. Now, this is very crucial. Similarly, in fact, that entanglement, etc., quantum entanglement is all because of this thing. Conversely, any two or more states may be superimposed to give a new state. So this is the, you can say, the heart of quantum mechanics. You have to keep this thing in mind. And I will explain this superposition principle. Okay, so let us try to understand the superposition principle because this is very crucial. If you understand superposition principle, most of the concepts of quantum mechanics are clear. And this experiment it can be done easily. What is the experiment? Understanding polarization light in terms of photons from superposition principle. Now, see, this is something very interesting because light polarization is a wave phenomenon, but I am trying to understand in terms of the photons. That is why I said that once you understand superposition principle, then all doubts about wave particle duality are gone. Okay, light gets polarized, so it's fine. Nobody had disagree because we can do an experiment about that. Light consists of photons. ये भी prove कर दिया हमने photoelectric effect से. Photons are also polarized as can be checked by the preferential emission of electron in the case of photoelectric effect. So photon can also get polarized, right? So these two are experimental fact. Consider tourmaline which permits plane polarized light which is perpendicular to its optic. This is the tourmaline crystal and it permits light if it is polarized perpendicular to the axis. This is the optic axis. ठीक है, ये एक्सपेरिमेंटल ऑब्जर्वेशंस है. अब इसको हमने समझना है इन टर्म्स ऑफ फोटॉन्स एंड सुपरपोजिशन प्रिंसिपल. वो कैसे समझेंगे हम? Okay. Polarized, suppose light is polarized perpendicular to axis, light passes, कोई उसमें इश्यू नहीं है क्योंकि हमने ऑब्जर्व किया ये. Polarized parallel to axis, no light goes through, there is no problem. Problem is polarized angle alpha to axis. So if it is polarized at an angle alpha, as I shown in the previous slide, then sin alpha square passes. Then what we find, some part of the, I think there is a, go to the, okay, so okay, so what I should say is that only part of the light passes, not the all the light passes. Now, beam consists of photons which are polarized for parallel perpendicular. There is no problem. What will happen to each photon as it approaches Tomlin? Not a precise question to ask. To make it precise, one must imagine experimental performed having a bearing on the question you ask. Now, this is what's the heart of physics. If you have a physical question, then corresponding experiment has to be there. If you cannot design a corresponding experiment, then that question has no validity in physics. ये कोई बंदा बात नहीं करता फिजिक्स में सारे क्वेश्चन का जवाब नहीं दे सकते हम उन्हीं क्वेश्चन का जवाब दे सकते हैं जिनका कॉरस्पॉन्डिंग एक्सपेरिमेंट कर सकते हैं. दिस इज व्हाट इज टू बी अंडरस्टूड. नेक्स्ट, only question where the results have real significant question that certificate has to answer. Okay, so how do we explain it? No, if you have a single photon, if there is a beam of photons, no problem. We can say if it is polarized at an angle, some photon, some part of the beam passes, but then light consists of photons. That means in principle, I can carry the same experiment with a single photon. And incidentally, these days we can have single photons also. Those who do atomic physics, they know about it. Okay, so let us try to see how we understand that. In case of a single photon, sometimes photon and sometimes nothing is there. Photons, okay, determination of classification is no longer there. What we can say is that we can predict set of possible result with probability occurrence for each. To understand the result, we postulate that photon is partly in state parallel and partly in perpendicular state. That means this is the photon. It is expressed in terms of parallel polarization and perpendicular polarization. These are the two basic states, right? In which a photon can be there. Either it can be parallel polarized or it can be perpendicular. Alpha, beta, two complex number. When we make the photon meet tourmaline, we are subjecting it to observation. We are observing whether photons are polarized parallel or perpendicular to the axis. The effect of observation is to make the photon jump from one state to another. Which of the two states will jump? We cannot say, but we can talk only about the probability. In fact, this is also this is old language. 40-year-old or 50-year-old, when people used to say that when you make an observation on a quantum state, then it jumps from one eigenstate to another eigenstate. I would, in the present context, I would say that if you make an observation on a photon which is polarized at an angle alpha, then you will observe two results. Either sometime the photon passes, sometime the photon doesn't pass. We can predict only the probability with which it will pass and the probability with which it will not pass. So alpha mod square, which is corresponding to the, you can say the perpendicular polarization. So what you will observe, if you conduct an experiment at an angle which is alpha with the axis of the tourmaline, then you will say sin square alpha times the photon passes. If you do n number of times, then n sin square alpha times you will observe that the photon passes, and n sin square alpha, it doesn't pass or it is gets absorbed by that. No, no, this is the, you can say what I have done. It looks very simple actually, but most of the concepts I've already covered. In quantum physics, the eigenstates concepts come. I've talked about the two eigenstates. I have talked about the superposition of eigenstates of photons. Actual experiment can be conducted in the observation. What we find, I have talked about the photons. No, I talk only about photons. In fact, the entire electromagnetic phenomena can be explained in terms of photons. So you don't have to worry about whether it is a particle or a wave. No, let me tell you where the confusion rises. When you say that the electron is a wave, I remember that I attended a seminar 50 years back when I was a student, young student, a very prominent person was talking. I say, sir, if it is a wave, where does its charge lies? He didn't know how to answer that. The reason is simple because as a student, I imagined that a wave means it's a wave. So how can you call it a particle? He should have said, well, when we throw an electron and scatter it, then its interaction reflects the wave-like characteristics. Because when the electron were, you can say, scattered from array of atoms or crystals, we found that a pattern which was similar to diffraction pattern. Similar to diffraction pattern. It was not the diffraction pattern, similar to diffraction pattern, and that gave rise to, because physicists had no other language, they started saying it's a wave particle duality. But actually, इस सुपरपोजिशन प्रिंसिपल, अब नया इंटरेक्शन को एक्सप्लेन करने के लिए आपको नई चीजें अज्यूम करनी पड़ेंगी. At least to me it seems there is no paradox involved in this. Classical physics में हम कोई चीज ऑब्जर्व करते हैं, क्वांटम फिजिक्स में जाते हैं तो हमें नए मैथमेटिकल फॉर्मूला निकालने पड़ेंगे, एंड दैट इज व्हाट वी हैव. एंड वन हैज टू कीप इन माइंड देयर आर इनहेरेंट लिमिटेशन एज फार एज ऑब्जर्वेशन आर कंसर्न. एंड व्हाट आर द postulates? The postulates of modern theory of quantum mechanics is the state of a quantum mechanical system completely specified wave function psi that depends on the coordinate particle and on the time. The function is called as a property that psi. This is the probability that particle lies in the volume delta tau located in time t. This is the fundamental starting point. You have to start with that. That if you integrate on the whole space, the probability has to come to 1 if the wave function is normalized. Those who already study the wave function, right? This has to be the starting point. If an electron is there in the entire universe, if you do the integration, it has to be there, and the probability has to be 1 that it has not gone out of the universe. And you know that when do the integration, they tell you that go from minus infinity to infinity, or you can cover the entire space. With every physical observable Q in classical mechanics, there is associated with linear Hermitian operator Q in quantum mechanics. In any measurement associated with the observer, measurement means when you have an operator is acting on the state. That means you carry on an observation, whether you are measuring energy or momentum, whatever you can measure in a consistent manner. Like you can, position you cannot measure in a consistent manner along with momentum. So you have to have momentum and energy and other spin of the system and so on and so forth, or angular momentum of the system. You make those, then there is an operator, and that operator acts on the state. That is a result Q, which is a eigenvalue equation. This is called the eigenvalue equation. And then of course you have the set of eigenvalue operator will form a complete. Yeah, that's a little complicated. Let me not get into. For a system described by given wave function, the expectation value on your property Q can be found by the expectation value of the property Q can be found by expectation value integral with respect to wave. These are the postulates which are well known, and of course this is the Schrodinger equation, the time evolution of wave function, how the wave function will evolve with time given by the Schrodinger equation. So this is all about the quantum mechanics. No, the crucial point is we are in a different regime. Now let me summarize. I started with the fact that physics depends on the observation process, and there is always a limitation of observations. The domain of observation determines your theory. Theory is a hypothesis. It is not something given by God. It's a hypothesis which will change if the domain of observations increase. और सबसे बड़ा एग्जांपल मैंने आपको सिंपल लाइफ से दिया, चाहे सोलर सिस्टम है, चाहे ट्रेजर, or you can think of any other example, many examples from your life. If the domain of observation change, you start observing newer phenomena. And if the newer phenomena are observed, no wonder that you have to make new hypothesis. अब क्वांटम मैकेनिक्स में उसको मैथमेटिकली डिस्क्राइब करने के लिए आपको कुछ चीजें assumption करनी पड़ती हैं. अब ये हिट एंड ट्रायल से होता है. ये जो मैंने इतनी 1 घंटे में आपको क्वांटम मैकेनिक्स बता दी है, वो ऐसे नहीं डेवलप होती है. ये 20 साल लगे इसको, सब तरह के ऊट पटांग क्लासिकल इक्वेशन, ये इक्वेशन सब कुछ ट्राई किया लोगों ने। जब कुछ नहीं बना तो फिर ये श्रोडिंगर इक्वेशन आई। ये सारी चीजें बाद में आई हैं जो मैं पढ़ा रहा हूं आपको। इट टुक ऑलमोस्ट another 20 years of the quantum mechanics to reach at these firm conclusions. The crucial point is कि जब डोमेन ऑफ ऑब्जर्वेशन बदल गया आपका, तो नए फिनोमेना तो ऑब्जर्व होंगे ही होंगे। अब मैं आपको एक दो एक्सपेरिमेंट और डिस्कस कर लेता हूँ। यंग डबल स्लिट एक्सपेरिमेंट, जो सबसे बड़ा कंफ्यूजन क्रिएट करता है, क्योंकि कैसे दिखाते हैं बुक्स में कि दो स्लिट्स हैं, इलेक्ट्रॉन पास कर रहा है उसमें से। क्लासिकली तो वो एक स्लिट से पास करे या दूसरे से करेगा। quantum mechanically they say electron can pass simultaneously from both the slits. No, this is nonsense, in the sense you have to have a microscopic double slit. How do we make microscopic double slit? It is a collection of atoms and molecules, and that simple example is the crystals. Crystals are the double slits actually which they talk. उसको ड्रामेटाइज करने के लिए आज से 100 साल पहले लोगों ने डबल स्लिट सोच ली कि लाइक ए क्लासिकल डबल स्लिट। इट इज क्रिस्टल, एंड क्रिस्टल्स में क्या हो रहा है, इलेक्ट्रॉन इज स्कैटरिंग फ्रॉम द डिफरेंट प्लेसेस। वो स्कैटर कर रहा है, उसका इलेक्ट्रोमैग्नेटिक इंटरेक्शन है। इलेक्ट्रोमैग्नेटिक इंटरेक्शन एक, अब आई कैन एक्सप्लेन थ्रू क्वांटम फील्ड थ्योरी आल्सो। अब हाउ डज द इंटरेक्शन बिटवीन इलेक्ट्रॉन एंड photon take place? Actually, electron is not a sitting charge. It is emitting and absorbing photons all the time. It's a dynamic system. If there are two electron proton are interacting, that means they are exchanging photons. Sometimes a real photon is exchanged. That means the energy exchanges between them. They are always emitting and absorbing photons within the purview of uncertainty principle, because we cannot measure the energy with time correctly, energy and time at the same time. Therefore, there is always a possibility of what are called quantum fluctuation. In that fluctuation, the model is that the electron and proton can exchange some energy through the exchange of photons. Now, this is the model. अब जब आप ये scattering करते हो electrons की crystal से, so same thing is happening. और आपने डबल स्लिट इमेजिन ही करनी है, तो आप उसको ऐसे इमेजिन करिए कि इट इज अ कलेक्शन ऑफ एटम्स एंड मॉलिक्यूल। No, if it is a collection of atoms and molecules, then the electron scattering is taking place. It is not that the physical trajectory is passing through that, and that is creates the problem. तो इसलिए कोई ऐसा ये डबल स्लिट वगैरह का अभी भी मैंने देखा है। मैं 2 दिन पहले वीडियो देख रहा था। I was shocked and surprised कि still people are talking about that double slit experiment, which creates havoc in the minds of the students. Keep in mind, it's a scattering experiment. The double slit is not like classical double slit. It is a collection of atoms and molecules. And when you are considering collection of atoms and molecules, electrons are scattering from there. And once they are scattering, there's always a diffraction pattern associated with that. इसको और डिटेल में एक्सप्लेन कर सकते हैं, बट फॉर दैट वन हैव टू अंडरस्टैंड क्वांटम फील्ड थ्योरी एंड सो ऑन सो फोर्थ. सो आई थिंक आई हैव कवर्ड most of the points, but questions are welcome. So that is where the student can ask me any question. See, don't bother if you have not understood anything. Still, you can ask question. These are things which even the experts don't understand. They look very simple. अब मेरे को कहोगे मैंने भी तो बहुत सारी झक मारी है तब जाके यहाँ पे पहुंचा हूँ. Otherwise, when I was student, I was also very much confused. क्योंकि जिस टीचर से पूछो वो भी. अब मैं आपको एक छोटा सा एग्जांपल भी दे देता हूँ. My teacher, of course, I have greatest regard for my teachers, because not teachers are not gods. They tell you a lot of things which are correct, but they may tell you something which may not be fully correct. I'm not saying wrong, fully correct. So he was teaching us wave particle duality. He says a particle is like, suppose you are assuming a bird sitting on a tree, and it is its wings are folded, so it's particle. Once the wings open, it becomes a wave. No, this is something I would call it very crazy. This is what creates havoc in the minds of the student. But no wonder that the quantum mechanics remains misunderstood, because the books are written like that. When people do quantum mechanics, they understand it. But when they write quantum mechanics, they don't write it properly. This is a problem. And the language also is not at times appropriate. As I mentioned, we should have written dual in quotes. We should not have written dual behavior in quotes. Similarly, other things, observations, what is the meaning of observation, and so on and so forth. So any questions, most of the questions are welcome to ask me.
Hello. First, thank you, sir, for the wonderful talk. Yes, any question from student? Any question related to quantum mechanics? Sir, first, I want to ask one question.
Yeah, surely.
Is there any boundary between classical and quantum physics?
Is there any?
Boundary between classical and quantum physics?
Yes, actually, I would call it as there is no boundary. It is continuous. When you are in a macroscopic domain, then you have very good approximation in terms of electromagnetic laws and you can say Newton law, right? But as you go down, in fact, you can derive these electromagnetic laws and Newton law from quantum mechanics, right? But there is no advantage of doing that. You will waste a lot of time. At the end, our Newton laws works very well for macroscopic object. Why should I derive it from quantum mechanics? The correction will come at a very, very deep level. आप 15वें डेसिमल प्लेस पे करेक्शन ढूंढ भी लोगे तो करोगे क्या उसका? So classical mechanics within its domain is working perfectly. Quantum mechanics within its domain is working, right? So बीच के डोमेन में आप क्वांटम मैकेनिक्स भी यूज कर सकते हो, क्लासिकल भी यूज कर सकते हो. इसलिए नैनो साइंस में आप देखोगे दोनों चीजें यूज होती हैं. डिपेंड करता है आप कितने नंबर ऑफ ऑब्जेक्ट पार्टिकल इज लार्ज, यू आर 10^8 or 10 particle, you can use classical mechanics also or classical physics, and then some effects you can calculate through quantum effects also. But when the number of particles becomes small, say maybe 100 or 200 or even 1000, then quantum effects become very important. So it is a continuous kind of thing. Physics remains the same, but in this domain, quantum mechanics applicable होती है. आप दूर चलेगा तो बेटर है कि क्लासिकल फिजिक्स लगभग और ग्रांट देती है वो. See, मैं कभी नहीं कहता कि क्लासिकल फिजिक्स रॉन्ग हो गई. क्लासिकल फिजिक्स इज स्टिल राइट. क्लासिकल इक्वेशंस ऑफ मोशन तो डेटाबेस है, वो डोमेन में तो वैलिड है भी. तो यू कैन यूज दैट.
Thank you, sir.
तभी तो दैट इज व्हाई द इनर लार्ज पार्टिकल लिमिट क्वांटम मैकेनिक्स रिड्यूसेस टू क्लासिकल. ये वो क्या कहते हैं अपना एक थ्योरम यूज करते थे ना. हाँ, वो स्टूडेंट्स में.
Thank you, sir. Yes, any question from audience?
अब जितने मर्जी क्वेश्चन पूछो, सही गलत क्वेश्चन पूछना भी एबिलिटी होती है, वो डेवलप करो एज स्टूडेंट्स.
Good afternoon, sir. First of all, thanks a lot for such an amazing lecture. My question was that every classical body can be divisible into small bodies at quantum level. So why do we observe quantum effects at only atomic level?
Yeah, what is the question exactly? Can you come?
Sir, the classical bodies can be divisible into small bodies at atomic level. Then why do we only observe quantum effects at atomic level?
आप थोड़ा बताओगे, मेरे को थोड़ा हियरिंग में इशू होता है.
Actually, sir, she is asking about the divisibility.
नॉइज की वजह से प्रॉब्लम आती है.
So my question is that every classical body can be divisible into smaller bodies. Like every body is made up of atoms. So why do we observe quantum effects at only atomic level and not classical levels?
See, it's very simple. वो मेरी पहली तीसरी चौथी स्लाइड में आंसर दे दिया है. When the disturbance, ऑब्जर्वेशन का मतलब क्या है? ऑब्जर्वेशन का मतलब यह है कि आपको कोई एक्सपेरिमेंट कंडक्ट करना पड़ेगा. एक्सपेरिमेंट कंडक्ट कैसे करते हो? आप कोई चीज फेंकते हो, उस पर मोस्ट जनरली लाइट फेंकते हैं हम, और कोई एक्सपेरिमेंट भी कर सकते हैं. अल्टीमेटली यही होता है. ऑब्जर्वेशन आप कुछ भी कर लो, आप फोटो, आप कैमरा खींचते हो, कैमरे में तो यही होता है ना. तो कोई भी एक्सपेरिमेंट ले लोगे यही होगा अल्टीमेटली. अब उसमें क्या है कि व्हेन द डिस्टर्बेंस is of the order of the object to be observed, or when the energy of the observing tool is of the order of the object itself, then we are in a quantum domain. क्लासिकल फिजिक्स में जो है मैक्रो ऑब्जेक्ट को डिस्टर्ब नहीं करता, उसको वी मेक दैट. तो उसको वो ऑफ कोर्स इट इज मेड अप ऑफ स्मॉलर ऑब्जेक्ट्स, बट स्मॉलर ऑब्जेक्ट को सिर्फ स्मॉलर ऑब्जेक्ट को ऑब्जर्व करें. देन वी हैव टू यूज क्वांटम. If you have to observe larger object, then there's no issue, right? Is that clear?
Yes, any other question?
हाँ इधर आ जाइए, इधर आ जाइए. इसी से बोलिए ताकि बाकी बच्चे भी सुने.
So you have told about the Young's double slit
Hello.
experiment. You have told about Young's double slit experiment earlier now only. So can you please explain ki how that is wrong? I have not understood about ki how you would say.
करिए क्वेश्चन अपना.
So that how Young's double slit experiment is wrong.
यंग डबल स्लिट एक्सपेरिमेंट में गलत नहीं कह रहा. व्हाट आई एम सेइंग इज कि ये एक पिक्चराइजेशन लोगों ने बना दी थी कि यंग डबल स्लिट एक्सपेरिमेंट में क्वांटम मैकेनिक्स की मिस्टीरियस बनाने के लिए कि क्वांटम मैकेनिक्स कैसे एक्सप्लेन करते हैं. आप पढ़ लीजिए बुक्स जाके कि इलेक्ट्रॉन की बीम है स्पेसिफाइड एनर्जी की, देयर इज अ डबल स्लिट एंड क्लासिकली वो इलेक्ट्रॉन या तो एक स्लिट से पास करेगा या दूसरी स्लिट से पास करेगा. सो यू विल ऑब्जर्व टू बीम्स, राइट? But quantum mechanically, what you observe is you observe a spectrum, right? So that's why it's a wave, and its wave can pass through wavelets, right? वो उसके wave fronts करके फिर interference करते हैं. But it doesn't happen that manner. अब जो हमने ये explain किया है, आप इसको understand करिए कि actual experiment क्या होगा. Actual experiment ये